dive into the heart of reality, where the rules of the macro world no longer apply. Imagine a realm where particles can exist in multiple places at once, communicate instantly across vast distances, and even flip between matter and energy. This is not the stuff of science fiction, but the very real and utterly mind-bending world of quantum physics. We're about to explore entanglement, superposition, tunneling, and more. Welcome to the quantum realm, a world of infinite possibilities and the key to understanding the universe's deepest mysteries. Imagine two particles, no matter how far apart, responding to each other instantaneously. Welcome to the fascinating world of quantum entanglement. In this realm, two particles become entwined in such a way that the state of one immediately influences the state of the other, regardless of the distance between them. It's as if they're two halves of the same whole. This phenomenon, once dubbed spooky action at a distance by Albert Einstein, has profound implications. It could revolutionize communication, allowing for the transmission of information at speeds far exceeding what we're used to. Imagine, for instance, a future where messages are sent halfway around the world in the blink of an eye, without any delay. Moreover, quantum entanglement is the foundation for quantum computing, promising to solve problems that today's most powerful supercomputers can't even touch. This spooky action at a distance defies our everyday understanding of the world. Is it a particle? Is it a wave? In the quantum world, it can be both. Let's take a moment to ponder on this question. How can something be both a particle and a wave? It's a bit like asking, can something be both a car and a boat? In our everyday world, the answer is a resounding no. But in the quantum realm, the rules are different. This is what we call the wave-particle duality. It is the idea that every particle or quantum entity may be described as both a particle and a wave. Historical experiments, such as the famous double-slit experiment, have demonstrated this bizarre characteristic of light and matter. So why does this matter? Well, wave-particle duality has far-reaching implications in technology. It forms the basis of quantum computing and quantum encryption, technologies that may revolutionize our world in the future. This dual nature of light and matter is one of the cornerstones of quantum mechanics. In the quantum world, precise measurement becomes a game of chance. Enter the Uncertainty Principle, a cornerstone of quantum physics proposed by Werner Heisenberg. This principle asserts an inherent limit to the precision with which we can simultaneously know the position and momentum of a particle. Imagine trying to track a hummingbird in flight. The more precisely you try to pinpoint its location, the less you know about its speed and vice versa. This isn't due to any technological shortcomings, but a fundamental aspect of nature itself. The uncertainty principle shatters our macroscopic understanding of reality, where we can, for example, know both the speed and location of a moving car. In the quantum realm, reality becomes fuzzier, less definite. This principle redefines our understanding of reality, pushing us to rethink what it means to know something. The more precisely we know one quantity, the less precisely we know the other. A particle in multiple states at once? Welcome to quantum superposition. Now, this may sound like something out of a science fiction novel, but it's a cornerstone of quantum physics. Imagine a particle that can be in two places simultaneously, or a cat that's both alive and dead at the same time. This isn't your regular logic, it's quantum logic. Quantum superposition tells us that, until measured, quantum entities can exist in multiple states or places simultaneously. It's like having a coin that's both heads and tails at the same time until you look at it. Baffling, right? This concept isn't just theoretical, it's at the heart of quantum computing, where quantum bits or qubits, unlike classical bits, can be both 0 and 1 at the same time. This allows quantum computers to perform complex calculations at speeds unimaginable with today's technology. Quantum superposition also plays a crucial role in quantum encryption, enhancing the security of information transmission. Reality, as we know it, is challenged by this bewildering yet fascinating concept. Defying barriers and classical physics, we present the enigma of quantum tunneling. Imagine a ball rolling up a hill. According to the laws of classical physics, the ball would need a certain amount of energy to get over the hill. Without it, the ball simply won't make it. But in the quantum world, things work differently. Here, our quantum ball can do something downright magical. It can tunnel through the hill appearing on the other side without ever having climbed over the top. This is quantum tunneling, a phenomenon where particles can pass through barriers that in the classical world would be insurmountable. Quantum tunneling isn't just a fun thought experiment, it plays a crucial role in many aspects of our daily lives. For instance, it's responsible for nuclear fusion within the Sun, the process that powers our life-giving star. And it's also at play in the functioning of our electronic devices. This quantum phenomenon powers the Sun and our electronics. Fields permeating space, particles as excitations. Welcome to quantum field theory. Quantum field theory is the language of the quantum world, a framework that paints a vivid picture of reality at its most fundamental level. In this theory, fields are the foundation of everything. They crisscross the entire universe, permeating every nook and cranny of space. Particles are merely the manifestations, the excitations of these fields. Imagine a calm ocean. The waves that you see are like particles, disturbances on the otherwise tranquil surface. That's quantum field theory in a nutshell. But there's more. Quantum field theory is also a unifying force. It's the theory that brings together electromagnetism, the weak nuclear force, and the strong nuclear force, the fundamental forces of nature under one roof. This theory brings us closer to a complete understanding of the universe. It's an essential piece of the quantum puzzle, a stepping stone towards the ultimate theory of everything. Quantum physics is not just theory, it's shaping our world and future. From the minute to the monumental, the impact of quantum physics is being felt. Let's dive into some real-world applications. Medical imaging technologies such as MRI and PET scans owe their precision to quantum mechanics. These life-saving tools use principles of quantum physics to create detailed images of our bodies, helping doctors diagnose and treat illnesses more effectively. The world of technology also benefits immensely from quantum physics. Quantum sensors, for instance, are elevating our ability to measure physical quantities to unprecedented levels of accuracy. They're revolutionizing fields like geology by enabling precise measurements of gravitational fields, aiding in the discovery of natural resources and monitoring seismic activity. Now let's peer into the future, where the quantum realm promises even more remarkable breakthroughs. Quantum computers, still in their infancy, hold the potential to revolutionize computing, cryptography, and problem-solving. They could outperform classical computers in tasks like factorizing large numbers or simulating complex quantum systems, opening up new horizons in fields such as drug discovery or climate modeling. And then there's the tantalizing prospect of quantum teleportation. While we're not quite ready to beam humans Star Trek style, scientists have successfully teleported information between particles. This could lead to ultra-secure communication networks and lay the groundwork for a quantum internet. As we harness the power of the quantum world, the possibilities are limitless. The quantum revolution is already here and it's only just getting started. So buckle up, because the future is quantum. Let's take a moment to revisit our journey into the quantum realm. We started off by exploring the concept of quantum entanglement, where we found that particles can connect in a way that transcends space, making instantaneous communication a tantalizing possibility. We then dived into the Wave-Particle Duality, a phenomenon that shows us how light and matter can behave as both particles and waves, challenging our conventional understanding of the physical world. Next, we tackled the Uncertainty Principle, a cornerstone of quantum mechanics that asserts the impossibility of precisely measuring both the position and momentum of a particle. This principle nudges us to rethink our perception of reality, reminding us that certainty in the quantum realm is an illusion. We then ventured into the world of quantum superposition, where particles can exist in multiple states at once until observed, a concept that holds enormous potential for revolutionizing computing and encryption. Quantum tunneling was our next stop, a process that allows particles to pass through barriers, defying classical physics and playing a crucial role in nuclear fusion and electronic devices. Our exploration then led us to the many worlds interpretation, a mind-bending theory that proposes the existence of parallel universes, challenging our notions of reality and identity. We also delved into quantum decoherence, which provides a bridge between the quantum and classical worlds, explaining the transition from quantum systems to the observable reality we live in. We then examined quantum computing, a revolutionary technology that leverages the principles of quantum mechanics to process information in ways that classical computers can't, potentially transforming cryptography and problem-solving. And lastly, we looked at quantum field theory, a framework that depicts particles as excitations in fields permeating space, a theory that's key to unifying the forces of nature. This journey through the quantum realm has shown us how quantum physics is not just a theoretical curiosity, but a practical tool that's already shaping our world, from medical imaging to quantum sensors, and holds the promise of future breakthroughs. As we peel back the layers of the quantum world, we edge closer to understanding the fabric of reality itself. What secrets will we uncover next?